Okay, we're back, we're live. It's still Monday. It's going to continue to be Monday all day, actually. And we have Mark Rognstad, project engineer at the University of Hawaii at Manoa, the Hawaii Mapping Research Group. And if I made an acronym out of that, it would be HMRG. RG. Humrug.
Yeah, we usually don't try to pronounce it.
Sorry, I even tried. So, and you're with SOEST, of course.
That's right.
And so we need to find out more about the world around us, and SOEST does that, and you do that with SOEST. Mm-hmm. So the question is, how do I get your job, Mark? What do I have to do and study, and how do I spend my life to arrive at where you are?
Well, in college, originally I was going to study a major in physics and electrical engineering. But at that time, which was back in the early 70s, in electrical engineering, there were sort of two paths. One, the standard electrical engineering where you study power transmission and generators and antennas and that kind of stuff, or computers, which was all software and operating systems. And what I was and still am the most interested in is digital electronics, sort of the hardware of computers. And there wasn't a program for that. So I ended up just majoring in physics. And then by the end of my 4 years in undergraduate, I'd gotten pretty much all the requirements for a math degree too. So I double majored in physics and math. I went to grad school for just over a year and dropped out and came home and started looking for a job. Well,
I mean, at that point in your career, what were you qualified for?
Well, I had summer jobs working at UH, basically doing electrical engineering. Actually, for the most part, working on Sonar. Mm-hmm. Although almost all of that was building instrumentation and doing some programming tests in the lab. I never went out to sea during those summers.
You were a black box man. You took the black case there and did magic things with electronics. Is that what you did?
Well, I'd design what would go inside the black box.
Yeah.
So I saw an ad in the paper, and it was for a electronics technician at the Institute for Astronomy. And
IFA.
Yes.
IFA.
Mm-hmm.
To those who know.
Mm-hmm.
It's a lovely acronym. Now that's a good acronym, yeah?
Yeah. Another three-letter acronym, the TLA. So I got that job and was working for a group of planetary astronomers, initially on the instruments that we'd take to the observatory, mostly on Mauna Kea, but also sometimes to Kitt Peak in Arizona, and even once to the Johnson Space Center in Houston, where we're using these instruments to look at Apollo moon samples.
So can we stop for a moment and talk
Sure.
about the instruments you're referring to?
Sure.
Okay, they're electronics, they're black box. You have to have some familiarity with electrical engineering and maybe a little physics to know how this thing works. And it's sonar.
Well, no, at IFA, they were optical instruments. They measure light.
Measure light.
Right.
And you're not bouncing a light out and coming back. You're looking at light coming in.
Right.
It's a one-way street.
Right. Light collected by a telescope. So these instruments would mount on the back of a telescope. In the very early days, you would be standing there looking through an eyepiece in this instrument and guiding the telescope. And you would direct the light that you want to measure. For the instruments that I used, it was mostly planetary surfaces. We'd look at the moon and Mars and Jupiter.
So optics.
Yeah.
So you're collecting the light through a lens of some kind.
Mm-hmm.
And then you have what do they call it? A chip. It's a chip.
Well,
it's like my camera. It's like my...
This was before the days of chips.
Okay. Whoa, okay.
So,
what year was this?
This would have been starting in 1977.
Oh, that was a long time ago.
Yeah. So we used Vidicons for imaging.
Which is?
It's a vacuum tube.
Okay. Oh.
But mostly we were making just point measurements with things like photomultipliers and
It's a photocell. Is that what it is?
Well, it's kind of a photocell on steroids.
Okay.
It has a photocathode, this surface where when light hits, it knocks an electron free.
Okay.
And then there's a series of anodes that are sort of cascaded beyond that, and those are coated with a material where if an electron hits it, it'll knock a couple more electrons out.
Yeah.
And so it goes through this series of amplification, each one knocking more electrons off until finally you get a pulse of electrons coming out of the tube.
Which measures the intensity of the light.
Yeah, it basically would say a photon just hit. So you'd be counting photons,
Yeah.
as you'd be measuring individual photons of light.
And the more
coming through
photons
the
that hit,
telescope.
the higher
Right.
rate of whatever the
Right.
digital result. You're digitizing light. That's what
Yes,
it was.
yes,
right?
that's exactly
That was
right.
an early attempt to digitize light. It sounds like.
Well, yeah, I mean, the electronics that counted these pulses and recorded them were all digital. And then with these instruments, there would be filters that would filter out different wavelengths. And so you'd make a measurement with one filter, and then the instrument would move a filter wheel to bring another one into position, and you'd measure it at that wavelength.
What would the filter do for you?
Well, by looking at particular colors of light, you could get an idea of what the surface you're looking at is made of. So different minerals reflect light in different ways, and minerals look
This is
different
hot.
colors.
Now you can determine the elements on the periodic table of elements because of the light that's coming through
Well,
based on these filters. Am I right?
Yes, but even more than elements, you can also look at compounds, minerals that are made up of a number of different elements, and those will have characteristic reflectance spectra is what it's called. And that was the kind of technology that was used mostly looking through a telescope at planets. But we also, a couple of times, would take that with a small telescope over to the Volcano National Park and image rocks in cliff faces to determine what kind of lava made up the...
There it is. You learn it looking at one phenomenon, and then you apply it to another kind of phenomenon. And now you've put one side, the science covering both phenomena.
Right, right.
And now, what's the difference between, and you could probably tell me there's no difference at all, or there's a huge difference. What's the difference between what you're talking about, and hyperspectral imaging?
Well, it's basically the same. I mean, by imaging, you're creating an image.
A digital image of what you see and what you filter.
Right, right. And we did that with our Vidicon system, because that would use filters to pick out different wavelengths of light and then record an image. But with these photomultipliers, you're just measuring one spot, one pixel.
Yeah. But then you have to look at a lot of pixels and get a bigger image. I mean, or are we, when you do that, are you only concerned with the one pixel, or are you concerned with, making a composite of pixels?
Well, typically, the astronomer who, wants to use this data would pick out spots that are of interest. So we did a lot of work looking at the moon, and people would, well, we want to look at this mare or this crater. And so you'd point the instrument at that, collect the light from that, and you could record
answer a
that
question
information.
about it.
Yeah.
What about Mars? Did you see the movie?
No, I haven't
Well,
seen
you
it
gotta
yet.
go see the movie.
Yeah,
It's too
yeah.
good. It's too good.
Yeah, that's what I've heard.
Super science kind of thing,
Yeah, no, it sounds great.
And, I mean, and I think a lot of the things they know about Mars are based on this kind of examination, where it's not only that you're looking through light that has come, through the universe from Mars, but when you're right there.
Right.
I suppose what the science that you were talking about, I mean, and this is old science, we're going to update you in a minute, but the science of looking at light, examining light, and making conclusions about light could tell you lots of things about lots of things in the universe.
Oh, yeah.
I mean, it's everywhere to go, because light is everywhere. You can tell, my goodness, what you can tell. But let's update. Like I said, there you are with this old radio tube thing. I don't know if it's an accurate statement.
Oh, yeah.
And so now fast forward from the 70s till now, how have you gotten from there to here?
Well, the group that I work for had some funding cuts, and they had a number of engineers and technicians. And I guess maybe I should mention that after a handful of years, I got promoted to electronics engineer. But there wasn't as much money, and the head of the group came to me and said, there's another group here at the university that needs an electronics engineer. How would you like to work for them? And I said, sure, since, the alternative is not having a job, absolutely. So I called up the fellow that was the chief engineer for that group, and it was a Monday, and I said, are you interested in having me work for you? And he said, you already work for the university, that's great. Can you fly to Japan on Thursday? So 4 days later, I was on a plane
Pretty
going
exciting.
to Japan to meet a ship, one of the university's research ships.
Yeah.
And this sonar system that had been developed was being used off the shores of Japan.
Sonar is something that was new to you, or had you been working in sonar?
Well, it is new in that I hadn't worked with sonar before, but it has a lot of things in common with working with light.
Really? Can you talk about that?
Sure.
What's in common between sound waves and light?
Well,
Wavelength. Is that
yes.
right? Okay.
I mean, they're both waves. Light is an electromagnetic wave, and depending on the frequency, that will affect the color of light. And you can even expand beyond what we usually think about when we're talking about light, because all the way down to radio waves and infrared and up into X-rays, those are all different kinds of electromagnetic waves.
Right.
And light is just a little part of that.
Right.
Now, sonar is not an electromagnetic wave.
It's a physical.
It's a pressure wave.
Yeah.
So you've got, in this case, water, but it applies in air or any medium. Something forces the medium, and that compresses it a little bit, and that compression propagates through the medium and forms a wave. And just like electromagnetic waves, it's got a wavelength and it's got a speed, and you can use that to tell you things about what that wave is good for, good for detecting.
Is it like light where we were looking at, say, telescope light, and it was one-way street, or when you're talking about sound, you're always talking about a sonar two-way street?
Well, with the sonar, the kind of mapping that we do, it's always a two-way street. We're always sending out
But it
sound.
doesn't have to be.
No, it doesn't.
You can just be listening to sound that comes,
That's
for
right.
example, from a tsunami, I guess.
That's right.
Underwater
That's right.
or whatever. And the other thing is that the pressure aspect you mentioned seems like to me, and I'm really ingenue about it, light light doesn't push anything around. It merely is a waveform that comes through the universe at you. But when you're talking about sound, each pressure force is putting pressure on what's ahead of it. And so it's pushing. It's pushing the air, right? You need air for sound, right?
Right. Or water.
You got that? I want to be clear everybody got that, because we can't go any further unless you understand that you can't have sound without air or water or some other medium.
Yeah, there has to be a medium for the sound to propagate in.
Yeah. So the medium is being pushed. The sound is pushing the medium, and then the medium is pushing the next medium, and it just pushes everything through. That's a lot different than light, right?
Yeah.
Okay, so when you're talking about sound, you are still in the receiving business. At the end of the day, you're receiving it just like light. Is the engineering of your black box the same or different when you're looking at sound versus light?
Well, a lot of the engineering is the same, but the sensors that you use are different. The thing that converts that sound or light into an electrical signal is different for sounds and for light, and even sometimes different for different kinds of sound and different kinds of light. But once it's been turned into an electrical signal, Then, it's what we call a data acquisition system.
Yeah.
Back in the early days, they were built from scratch out of digital logic, but nowadays they're all based on computers.
Well, we have sound here.
Right.
You're making sound, I'm making sound. We have a new mixer which is reading all that sound and translating all that sound better than the old one, I can tell you right now today.
Great.
And you're the second guest who's been using the sound, so congratulations.
Oh, wow.
You sound terrific.
Thank you.
But it strikes me that we have a lot of technology about sound. That in a funny left-handed way, we have more technology, am I right? More technology about sound than we do about light. Why? Because of music. And we have been manipulating, sound waves in music to a fairly well for at least the last 50 years. I mean, since RCA and his master's voice, we've been playing with sound waves. Would you say that's right, or are we ahead of sound with light?
That's a really tough question. We've been working, humans have been working in sound for probably thousands of years, using it to create music. But as far as recording and manipulating sound, and recording and manipulating light, they're both pretty much, going back the last 100 years or so. It'd be a tough call to say which one we're better at. But if you think about music, that is, a pretty giant range.
It is. Music, because, I don't know why, but I'm thinking of Thomas Edison making his early videos. He had light, but he didn't have sound. The first, and he came out here. He made movies here.
Oh, yeah,
Hawaii,
yeah.
You can see them, some of them. Anyway, we're going to take a short break.
Okay.
And recoup. This is Mark Rognstad, project engineer at the Hawaii Mapping Research Group. And when we come back, we're going to find out about sonar and the seafloor. Because he's doing research with Marco Edwards, who sat in this very seat about a month ago. We're going to learn more about that. We'll see you in a minute. That's what we do.
Aloha, my name is Justine Espiritu, and I co-host Hawaii Farmers Series with Matthew Johnson of Oahu Fresh. We talk about Hawaii's local farmers and their supporters. In order to have a vibrant and sustainable local food system, farmers are always the foundation, but there's so many other people involved in the community that help support those farmers. So we bring those folks onto our show every Thursday at 4 p.m. We get their backstory, their history, find out a little more about them, and we find out why they love what they do and their perspective and their advice on how we can continue to have a dynamic and vibrant and sustainable local food system. So we broadcast live every Thursday at 4 p.m. And you can also catch us on ThinkTech's YouTube channel as well as Alelo 54. So we hope you tune in and join us. Thank you.
Okay, we're back. We're live. This is ThinkTech. This is Research in Manoa every Monday at 1 o'clock. And I am pleased to be able to interview Mark Rognstad, who is a project engineer with the Hawaii Mapping Research Group in SOEST, working with Margo Edwards there and working specifically on seafloor sonar mapping. We're calling this show Seafloor Mapping at SOEST. That's what we're doing. Okay, so all of this, it's really interesting how, sound and light, and now sonar, which is a sort of a double sound that you're doing on the seafloor. So how does sonar, how do you work with sonar? Is it the same kind of equipment as for sound itself? Or are there just two boxes, one that sends it and one that receives it? How does that work?
Well, for most of the mapping sonars, in fact, I guess for all of the mapping sonars, they produce sound. They put out a beam of sound, and that goes through the water and hits the bottom and then reflects off the bottom.
What does it sound like?
It's just a ping. For most of the systems that I work on, it's a higher frequency than you can hear. But you can.
Is there a reason for that?
Yeah. The higher the frequency, the shorter the wavelength.
Yeah.
And so if you use a low frequency, it's got a big long wavelength.
Yeah.
And instead of reflecting off of something, it will just diffract around it.
Yeah.
So in order to see more detail, you need to use higher frequency sound.
Got it.
It's kind of like, well, it's similar in light, using radio waves versus using infrared or visible light.
Interesting that this all came about in World War II, right?
That's right.
Because you had sonar and you had radar,
Mhm.
and it was pretty similar, wasn't it?
Very similar.
It's
Very similar.
pinging something, reading when it came back,
Mhm.
and making some calculation on the time it took to come back.
Mhm.
I mean, that in a very basic way.
That's exactly it.
Yeah.
That's exactly it.
Okay, so which came first? Was it radar or sonar? Radar is over the water and sonar is under the water, is that what?
Yeah. Radar is using radio waves. I think sonar probably came first, because I think that was actually being used in a very rudimentary way to track submarines in World War II, or World War I, rather.
Because we had no way to find out where they were. We couldn't see them.
That's
We
right.
couldn't necessarily hear them. We didn't have equipment to hear them. But if we had the ping effect, then we could find out where they were.
Well, you can hear submarines to an extent, and that's part of the challenge, because they do make noise. But if you're building a submarine, you want it to be as quiet as possible, so it's hard for somebody else to detect.
Yeah.
So there's what they call passive sonar that's just listening. And you can listen for submarines and surface ships, anything that's making noise. But if it's very quiet, or say your submarine is just floating in the water, it's not underway, then you need to send out sound to reflect off of it, to come back to you and tell you that there's something there.
Over the years, we've heard, I'm sure you've heard a lot more than me, about sonar having an effect on mammalian life underwater. Porpoises, whales, what have you. How does that work? And is it a serious physical damage to them?
It can be. It can be. I mean, whales and porpoises, cetaceans, they have sonar. They create sounds and listen for the reflections. They use sound to communicate with other.
So we interfere with their sonar. They have their sonar, we have our sonar.
That's true. That's true. There's interference, but with some of the sonars, actually both military and civilian, in order to map a large area, they've got to put out a very powerful sound. And if there are whales or dolphins that are too close to that, then their hearing can be damaged. And there have been cases of whales or dolphins that have been injured by these high-powered
Losing
sonars.
their hearing. And if they lose their hearing, they lose their ability to navigate in general.
Right.
That's pretty serious for them because
Yeah.
they depend on that.
Yeah.
So when you do a sonar, you do it at a high sound, a high volume, high level of sound. I don't want to say decibels, maybe that's the wrong.
No, that's
Is it
exactly
decibels?
what. Yeah.
So therefore, those decibels can be moderated in order to avoid damage or hearing loss to mammals who, do their own sonar.
Yeah. The thing about the kind of sonar systems that we built here at the university is that they're towed behind a ship. They're not attached to the ship, which is true of a lot of sonars. Like the echo sounder that you might have on your outboard is mounted on the hull, and it bounces sound off the bottom and tells you how deep the water is. But there's some advantages of towing a sonar behind the ship versus having it being attached to
You don't
the
have
ship.
the interference of the ship, for one thing.
Right. Ships are noisy.
Yeah.
But also-
Sure, they're noisy, but also the sonar bounces off the ship, right? Probably confuses the pattern.
Well, you design the sonar so that it projects sound in the direction you want.
So you point
can
it.
minimize.
So you have this kind of thing you tow, and it looks down at the bottom of the ocean, and it covers a broad area, because you have to have a broad area to do mapping, right?
Right.
And
right.
so, okay, so how broad is the area? And is it dependent on the depth of the ocean floor at that point, or can you control how broad it is, no matter how deep?
Well, it's both.
Okay. We're just trying to learn.
Yeah, yeah. I mean, the sonar system puts out a beam of sound that's kind of shaped like a fan. You want it to be thin in your along track direction, but wide in the cross track direction, because you're trying to paint a strip on the bottom with sound. And then you hear that sound reflecting back. Our lowest frequency system can put out a strip that's up to about 20 kilometers across. So it maps a big area. And it would be putting out another ping of sound in the ballpark of every 10 seconds.
That's not very frequent.
No.
You got to wait 10
problem
seconds
is
for
that
the next sound. Yeah.
sound doesn't go very fast, especially compared with light. It's 1,500 meters per second. So if you're trying to get a reflection from sound that's 10 kilometers away, you've got to wait for the sound to go all the way out there and come all the way back. And
So
actually,
you shouldn't go too fast on the ship.
Right.
Really? I'm guessing.
Yeah.
Nice and slow would be
Yeah.
fine, yeah.
But this system is designed for mapping everywhere in the ocean, as deep as the ocean gets. And in fact, the second deepest spot in the Marianas Trench was discovered by this system.
That's like 5 miles deep or something.
Well, it's a little more than 10 kilometers, so that would be like 6.5 miles.
6.5 miles.
Right.
And with your equipment that's towed behind one of the UH research vessels, they have long names that I can't remember.
Well, actually, we work off of a lot of ships, not
Okay.
just UH ships.
So it's at the end of the tow line, and it's being towed behind, and it can go 6 miles down.
Right, the sound.
The sound.
Right.
And does that mean that what kind of a pattern can you get? I mean, how broad, how large a pattern can you map when you're using this equipment in that way?
Well, you can map areas in typical research cruise might be about a month. And you can map areas that are the size of sort of average states. Many thousands of square kilometers. Because you're mapping a strip that's 20 kilometers wide, and you're going through the ocean at typically a speed of between 8 and 10 knots. So that's 16 to 20 kilometers per hour. So in 1 hour, you cover 400 square kilometers. And typically, when we're using the system, it's in the water. We're running it 24 hours a day, day after day. Unless something breaks and we have to pull it up and fix it, it might be in the water for,
A month.
yeah, basically the whole cruise.
Okay, that's Mark Rognstad, project engineer, Hawaii Mapping Research Group at SOEST, doing research at SOEST and doing sea mapping of the ocean floor at SOEST. We'll take one more break, and when we come back, I'd like to talk about what it looks like when you pull it out of the digital machinery. If we had it here, what would it look like? We'll be right back, you'll see, I promise. Yeah.
Aloha, this is Keli'i Akina, president of the Grassroot Institute, and I want to thank you for watching ThinkTech Hawaii. We are delighted to be partners with ThinkTech because it gives us the opportunity to bring to you a show every week on Monday at 2:00 p.m. called Ehana Kako. Ehana Kako means let's work together, because we believe that Hawaii will be a better place when everybody works together. And in what way? Well, at the Grassroot Institute, we research 3 basic areas, and we invite guests to come on board from across the country, the state, and the nation to talk about a better economy, a better government, a better society. Now, aren't those things we all want? Indeed. If you'd like to have the latest research in terms of public policy, as well as ways in which we can build a better government, economy, and society, then tune in every Monday on ThinkTech Hawaii at 2:00 p.m. for our fascinating guests on Ehana Kako. Let's work together. I'm Keli'i Akina with the Grassroot Institute, and I'll see you then. Aloha.
Bingo, I told you we'd be back. I wasn't kidding. Thank you, Mark, for staying with me.
You're
All
welcome.
right. It's Mark Rognstad, a project engineer at the Hawaii Mapping Research Service, rather group at SOEST, and we're talking about doing sonar floor mapping at SOEST, floor of the ocean. So when you get it back now through this stuff that you have designed, which I suspect is some of the most advanced sonar in the world, am I right?
Yeah.
Don't be modest. Yeah. Then you have a digital readout of the terrain of the ocean floor. Now, aside from terrain, what can you see down there?
Well, we produce two products, basically. One is how reflective the bottom is to sound, because things like rocks reflect sound real well, and things like mud don't.
So you can tell the composition of the ocean floor that way.
Right. And then the other thing is what's called bathymetry, the elevation of the seafloor. And the way that we do that is using something a lot like your own hearing. When the sound is bouncing back from the bottom, we're listening to it with two hydrophones, microphones for underwater, and they're separated by a distance, and it's just like your ears. So when you hear something, your ears will tell you, oh, the sound's over there, or it's over there. And the way that you do that is because it takes a different amount of time for the sound to get to each ear, and your brain can measure that.
The human body is an amazing piece of gear, isn't it?
Yeah.
You learn from the human body.
Right. And so we do the same kind of thing. You know, as the sound's reflecting back to the sonar vehicle, it's being recorded by two different receivers that are separated by a short distance. And so in the data processing, we can measure that
little
separation.
Algorithm. You wrote that algorithm.
Well, there's a number of people
Okay, all
that
right.
have worked with this. It's not just me.
Okay, so now it applies the algorithm, and again, it tells you, the terrain topography down there.
Right.
And then how does it reflect this? I mean, I know that at the end of the day, you have a kind of spreadsheet of data, database, which goes on for, thousands, millions of records with the digital read. But can you make a map?
Absolutely.
Yeah.
I mean, that is the deliverable.
Yeah.
Although you call them charts when they're in the ocean.
Yeah.
But we typically, while we are out at sea, process the data, turn it into these charts of both what we call backscatter, the reflectivity, and bathymetry, the depth. And sometimes people will like to combine the two by using color for bathymetry. So deeper places are, more blue.
It's not because they're blue down there, it's just because you use that to represent the depth.
Right.
Yeah.
And then you can make reflective things dark and, non-reflective things light. But for the most part, it's easier to sort of look at the data if those two things are separate.
Now, I know we spoke during the break, and I know you're working with a project that Margot Edwards has been involved with for years, and that is the munitions mapping to the southwest of Pearl Harbor.
That's right.
Where after the war, they used depth charge technology and dropped they disposed of unused munitions right, 20 miles away from Honolulu?
Or even closer.
Or even closer.
Yeah, and all kinds of munitions, not just depth
Mustard
charge.
gas comes to
Right,
mind as
chemical
an
weapons.
example. This is not a good thing.
And a lot of explosives.
Explosives, and not to say they will explode, but they may affect the flora and the fauna and the animals down there, because they'll ultimately seep through their canisters and make a mess. And ideally, one of these days we're gonna get that out of there, although that may take a real Herculean effort. But in the meantime, we have to know where it is.
Yeah.
And that's what you have been working on,
Yeah.
among other things.
Yeah, I mean, the first step really is to find out just, how big the problem is. And if you're going to even think about cleaning up something, you've got to know where to go.
Yeah.
So in the early parts of Margot's project, we did a bunch of mapping with our highest frequency system, with the highest resolution, because with that you can see the individual bombs or shells or depth charges sitting on the bottom. And one thing that makes it easy to pick them out is when those were being disposed of, typically they'd have a bunch of them on the deck of a ship, and they drive out from Pearl Harbor, and they'd start pushing them off the side. And so if you look at the map of the seafloor, you'll see these trails of,
It's a depth charge pattern.
it's like that,
It's
yeah.
a bombing pattern
Yeah.
kind of thing.
Yeah,
And so you can see this with your sonar.
with the sonar, that's right.
And if you can identify, because it'll be covered over with the schmutz down there,
Well, not
or
always.
will they be visible, in some other way?
Well, if they're actually buried, if there's around them, then we wouldn't see them with our sonar.
Mm-hmm.
There are lower frequency sonars that would actually penetrate the bottom. So you
Go
could
through the sand and
Yeah,
the sediment.
right. And I mean, very low frequency sonars that are very powerful are what are used for studying geology and finding oil, that kind of thing. They can penetrate
Long distances.
very long distances, right?
Like hundreds of yards, miles?
Oh, yeah, yeah.
Wow.
I mean, definitely hundreds of,
Long waves.
you're right,
Long,
Right.
powerful waves.
right. Because they're going down through the water, and then they're continuing into the earth and bouncing off layers.
Are you doing that?
No.
You're doing the shorter waves and the right on the floor rather than below the floor.
Well, we have built a sonar system that we can operate together with our other towfish that does some penetrating. It's called a Subbottom sonar. It's mostly penetrating maybe 100 meters. It doesn't go very deep. It's not super powerful, but it's of interest looking at layers of sediments. There was one survey that we were doing off of Mexico where there are places where gas bubbles seep up. And
Like methane gas.
right. And you can see in these sub-bottom images, you're going along and there's layers of sediments, and then all of a sudden the sediments are not layered anymore. It's just kind of all gray. And that's because bubbles have been coming up and sort of stirring the sediments up, and then you don't see the layers. And then you go along and there's more layers
So
again.
interesting. You go anywhere in the world, you
Yeah.
look at anything that anybody wants you to look at or that you want to look at for scientific purposes.
Mhm.
It's like the world is your sound oyster. You heard it here, I think.
Yeah, well, I've said that I've got one of the best jobs because I get to design cool, interesting things and build them, and then go all over the world with them and use them to help people find out more about the planet.
A couple, 3 years ago, the university was called to help by DBED, by the Department of Business Education, Business, Economic Development, and Tourism, for the undersea cable.
Right.
And what you're talking about sounds like it would be very relevant, useful to determine the path for an undersea cable for either electric, current or for video, I guess.
Yeah, communications.
Fiber communications, either way.
Yeah. We did some of the work for that, and we've done a lot of surveys for communications cables.
Yeah.
That is commercial work, and as a university, we don't, solicit commercial work, but there are commercial survey companies, and sometimes they will subcontract to us to use one of
But
our
they don't have the
systems.
technology they want the most advanced technology, and you have that.
Yeah, I mean, a lot of them have technology, but they have like sonar systems that will work in shallow water but not deep water. Or sometimes there's just so much demand that they can't do it with their own systems, and so they call on us.
Okay, so now I get to my favorite question, which I told you about at the beginning. So here I am, an ordinary person, ordinary workaday job, do my thing. Why do I care about what you're doing? How does it affect me?
Well, what we were just talking about, these communications cables, if you want to use the internet and look at websites on the mainland or in Russia or anywhere in the world, the odds are 99% of that is going over an underwater cable. And without a sonar survey to figure out where to run the cable, those would probably get broken very quickly.
Yeah.
If you lay it over like an active volcano, or even just a steep slope where
Yeah.
there's landslides,
Yeah.
that'll
Yeah.
break the cable,
Yeah.
very quickly.
So with these maps, you can find a comfortable path for the cable.
Exactly.
A
Exactly.
safe path for the cable.
Mhm.
And then you can show that to the cable layer.
Right.
And the ship that's laying the cable will know where to plant it,
Right.
down to a very fine tolerance. Yeah,
Right.
Yeah. So where's this science going to go? You've been doing it for a while. You must have in your mind, Mark, some future kind of state of affairs. Where is your science going 10, 20 years from now?
Well, there's an awful lot of the ocean that isn't mapped. I mean, people say, and it's true, that we know more about the backside of the moon than we know about the bottom of the ocean. I mean, people have a general idea of what the seafloor looks like, but for an awful lot of the seafloor, there's not very detailed charts. And so in order to find out about how the Earth works, having these charts is essential.
Yeah. We need to know how the Earth works.
Right.
And SOEST is so good at that. SOEST is the center of finding out how the Earth works and the ocean.
Mhm.
Thank you so much, Mark Rognstad.
You're welcome.
A Hawaii Mapping Research Group, research in Manoa, talking about mapping the ocean floor at SOEST with Sonar. Thanks so much.
You're welcome.